Hello everyone. Welcome to this course on industrial cybersecurity fundamental based on IEC 62443 framework. In this training series, we will explore how cybersecurity principles apply specifically to industrial environments such as manufacturing plants, energy system, and other operational technology environments. Before we begin, let me ask you something. What would happen if a cyber attack didn't steal data, but instead took control of power turbine, a manufacturing robot, or a water treatment facility? Cybersecurity in industrial environments is not only about protecting information, it's all about protecting the system that controls the physical world. Before we move further into this course, I want to briefly introduce the organization behind this training. This course is produced by CBOOMARANK, which is part of Cloud Boomer Technology. CBOOMARANK is a platform focused on providing intelligent analytical tool for website owner and digital professionals. Our platform simplifies the process of analyzing websites by providing SEO insights, performance analysis, and structured reporting tools. The platform allows organizations to evaluate their website performance, identify weakness, and make data-driven improvement. Our mission is simple: to provide tools and educational content that helps organizations understand technology better and make an informed decision. Alongside analytical tools, our company also produces educational cybersecurity contents, helping professionals to develop technical knowledge in areas such as cybersecurity, risk assessment, digital infrastructure, and also programming. And this course is part of that educational mission.
Well, as you can see from this screen, our website look like this. You can get it www.cboomarank.com.
If you are interested in learning industrial cybersecurity, IEC 62443, and real world security practice, you are exactly in the right place. On this channel, we publish professional cybersecurity training, practical tutorials, and step by step guidance designed to help you build real expertise in industrial cybersecurity and operational technology security. So, if you want to continue learning and stay updated with future training video, make sure to subscribe to this channel. You can find our channel here. Also, don't forget to click the notification bell so that you will notified whenever a new cybersecurity training video is published. And also, if you find this video useful, please consider liking the video and sharing it with others who are interested in cybersecurity. Now, let me briefly introduce myself. Well, my name is Akalilu Zawudu. My background is in computer science, engineering, and cybersecurity. I hold a bachelor degree in computer science engineering and master's degree in computer science. I have over 9 years of experience working in cybersecurity, including roles in penetration testing, vulnerability analysis, incident response, malware analysis, and security operations center environments. I have also worked as a SOC trainer, cybersecurity consultant, and operational technology or OT security advisor, helping organizations assess and improve security posture. In this course, I will guide you through the key concept of industrial cybersecurity and explain how standards such as IEC 62443, which is commonly called to be IC 32, are used to protect industrial systems. And we will approach this topic from both practical security perspective and standard-based framework perspective. Before we begin our technical discussion, it's important to understand what you will gain from this training. By the end of this course, you will understand several important concepts related to industrial cybersecurity. First, you will learn what industrial cybersecurity is and how industrial control system operates. Secondly, you will understand the structure and purpose of ISA IEC 62443, the cybersecurity framework. Third, you will learn how to secure architecture concepts such as zones, conduits, and defense in depth. These techniques are used to protect industrial networks. And finally, you will understand how organizations identify threats, vulnerabilities, and risks in order to implement effective cybersecurity control. This is how this course is structured. This training is divided into 5 focused episodes. Episode 1 introduces the fundamental of industrial cybersecurity and explain the difference between IT and OT environments. Episode 2 introduces the ISA IEC 62443 framework and explain how industrial cybersecurity governance is structured. Our episode 3 explores industrial cybersecurity architecture, including zones and conduits. Episode 4 examine security controls and risk management strategies. Episode 5 focus on implementation strategies and real-world industrial security practices. Each episode includes practical example, technical explanation, and certification style exam questions. This course help you both understand the concept and prepare for industrial cybersecurity certification studies. Let me ask you a quick question. When people first hear the name ISA/IEC 62443, most of them focus on numbers, but almost nobody stops to ask what ISA actually stands for. And surprisingly, that small detail tells us a lot about where this entire industrial cybersecurity standard comes from. You will often see this standard written as ISA slash IEC 62443, and it's important to understand what that actually means. The first part of the name, ISA, stands for International Society of Automation. This ISA is a global professional organization that focuses on automation, control systems, and also industrial operations. For decades, ISA has been involved in developing technical standards, engineering best practice, and professional training for industrial environment. But the story of this cybersecurity standard actually started under different name. The industrial cybersecurity framework we know called IEC 62443 was originally developed by ISA standard called ISA 99. This initiative was created to address a growing concern how to protect industrial control system from cyber threats. As the importance of industrial cybersecurity increased worldwide, the work developed by ISA was later adopted and published jointly with International Electrotechnical Commission, commonly known to be IEC. That collaboration is the reason the standard now called ISA/IEC 62443 comes. In simple terms, you can think of it like this. ISA provided the deep expertise in industrial automation, while IEC provided a global framework for international standardization. And so, for the IC32 certification exam, one key thing to remember from this is that ISA originally developed the industrial cybersecurity standard, while IEC helps publish and maintain it as a global recognized international standards. Now that we understand where the ISA/IEC 62443 standard comes from, the next question becomes even more interesting. How exactly is this standard structured, and how does it help organization to secure the industrial system? So let's explore that. Before diving directly into this, let's ask some important question. What exactly is industrial cybersecurity? Industrial cybersecurity focus on protecting industrial automation and control system, often referred to as IACS. That means industrial automation and control systems. This system monitors the physical world or the physical process control which an industry uses, such as for manufacturing, energy, transportation, and other utilities. Unlike traditional IT system, industry system interact directly with physical equipment. For example, industrial cybersecurity protects the building block of systems, such as a PLC or programmable logic controller, which executes a control logic, and also SCADA system, or a supervisory control and data acquisition, distributed control system, DSS, and also industry sensors and actuators, which connects the digital control system with a physical environment. We will see these key components of industry in the next slide. The main thing is industrial cybersecurity protects this the building block of industries. So a cyber attack on this system can have physical consequences, which makes their protection extremely important. Let us see this example. This example is intentionally simple, since industrial system control physical process and cyber incident cause operational impact, so safety and availability are critical and mostly important. Take this example. A manufacturing plant experiences a cyber incident, so no customer data is stolen, no email are leaked, yet the production stopped. So restarting the line safely takes hours. This means material will be wasted, schedules will be missed. So in our industrial cybersecurity, cyber incident do not need to steal data to cause a serious damage. In our OT environment, availability and safe recovery are often the most important concern. Now let us move to the operational technology. Operational technology represents a category of computing systems that monitors and control physical devices, processes, and events in industrial environment. These OT systems monitor and control the physical devices and industrial processes. They have OT technology, they have direct machine interaction, they work on real time, and also critical to any asset owner, country, or a government. For example, industrial control systems are operational technology. Those SCADA platforms, manufacturing automations, and power grid control systems, those are some example of operational technology. This operational technology have their own key behavior since they have their own priority. First priority in operational technology is availability, then reliability, and then safety. Unlike IT operation system, in IT they use CIA thread, confidentiality, integrity, and availability. We will see it together. Let's take an example on this. An OT monitors and control physical process and operates it in real time and directly affect machine and equipment. Let's take example. Temperature data is collected. For IT system, it will store the data for reporting or for sample space. While in operational technology, OT uses the data to open a valve or to shut down a process. So they have what we call that operational impact or in operational technology. Let me give you another example. For example, a power plant control system cannot simply be rebooted or restarted because of a software patch, because they have their own consequences, because they have uh, bad outcomes. Interrupting an industrial system could disrupt production, damage equipment, or even create safety risks. This is why cybersecurity strategy must be adopted specifically for OT environment. In this example, if temperature data is wrong in IT, a report may be inaccurate. If the temperature data is wrong in OT, the valve open or shut down. This direct cause and effect relationship is central to industrial cybersecurity risk. So it is now time to distinguish between IT versus OT. They have their own fundamental differences. Now, let's compare this with traditional IT environment. Information technology focus primarily on data processing and information management. Example of IT environment will include corporate networks, databases, email systems, web servers, and enterprise applications. In IT environment, the primary priority is confidentiality of information. While downtime is inconvenient, IT system can usually tolerate updates, reboots, and system changes. This flexibility does not exist in most OT or operational technology environments, because this leads to one of the most important concept in industrial cybersecurity. Uh, IT and OT system operate under very different priority and constraints. For example, IT priority in IT environments, the security model, as I have mentioned earlier, typically follow CIA traits: confidentiality, integrity, and availability. While in OT environment, the priority often looks like it's reversed. Availability and safety comes first. Uh, for example, if manufacturing line stops operating, production stop immediately. Because of this, industrial cybersecurity must balance security with operational continuity. So here, this is the major difference between IT and OT. Now let's move to where OT systems are deployed. Operational technology systems exist in many critical sectors. This includes manufacturing facility, power generation plants, electrical grid systems, and what we call is that renewable energy infrastructures. They have also include water purification plants and wastewater treatment facilities. In addition, process industries such as petroleum refining and chemical processing rely heavily on operational technology systems. This environment often operates continuously and also cannot simply be stopped for maintenance or security updates. So, this operational reality heavily influences how our framework or ISA/IEC 62443 approaches security. And now let's move to the key OT systems and components. What are the key OT system components? Industrial control system consists of several key components. Some of them are listed here. One component is programmable logic controller or PLC, which executes the control logic. Another component is human machine interface, which allows operator to monitor, process, and interact with the system. The other thing is supervisory control system, which commonly to be known as SCADA and DSC, which is distributed control system, which provides a centralized monitoring and control. SCADA stands for supervisory control and data acquisition. This system is focusing on high-level wide area network and data collection, while this SC or distributed control system is a process-oriented in system designed for real-time and complex control within a single local facilities. And finally, a sensor and actuator, which connects the digital control system with physical environment. So PLC execute and controls the logic, while human machine interface provide operator interaction. Sensor and actuator link to the physical world. For example, look at this scenario. A sensor sends incorrect data. It may be whether due to failure or attack. Then the PLC does not question the data because they simply execute the logic without any adjustment. So then it will execute the logic as designed. The result is unsafe in physical behavior. This scenario demonstrates why trust assumption matter. A sensor sends incorrect data, whether due to failure or attack. Then the PLC does not question the data, simply executes the logic without questioning. So it will execute the logic as designed. Then the result is unsafe physical behavior. An actuator perform an unsafe action. This is why OT cybersecurity emphasizes input validation, segmentation, and defense in depth. Now, let's move to the industrial control loop operation. In industrial system, this component operate together in what is known as a control loop operation. Since sensor measures the physical condition, the controller processes the data and executes the control logic, and actuator adjusts the equipment operation. This loop runs continuously in real time to maintain a stable industrial process. Let me give you an example on this. In this scenario, sensor measures the condition, then controllers process the logic, and actuator change or impact the process. In this scenario, the logic itself is unchanged, only the data is altered, yet the outcome is incorrect in physical behavior. For example, the sensor data is modified or delayed, control logic still runs, then physical process behave incorrectly. This highlights a critical concept of operational technology attack do not need to compromise the controller to be effective. Simply manipulating input can be enough to cause any tough problem to the industries. So now let's move to the security priorities. As we all know, in IT security, we have top priority, which is confidentiality, protecting the data from unauthorized access. But in most OT environment, priorities are different. As we can see from our presentation, in OT security priority, availability is the first. That means continuous operation without interruption. While in IT security priority, confidentiality must be the first criteria, since protecting the data from any unauthorized access. This may be applied on both sides, from sender and receiver. Integrity ensures data accuracy and consistency through various methods like encryption and also digital signature methods. And also thirdly, availability, system accessible when needed. These are the information technology security priority. While in OT security, as we have already mentioned earlier, availability is the first, since the operation must be done without any interruption. So the most important priority is availability, because system must continue operating. Second priority is safety, since failure can cause physical harm. And integrity ensures that industrial process operates correctly. This reversal drives nearly every operational technology security decision. If you remember one priority rule from this course, it should be this one. The OT security priority must be availability, safety, and integrity. So this is critical, exam critical priorities reversal, especially availability is the top concern in OT, and also it's fundamental to the our framework IEC 62443 implementation, and it's frequently tested. And now let me show you some example. Since availability comes first, safety is critical, and integrity supports safe operation. For example, ransomware hits an industrial system, then data loses bad, production loses worse, safety impact is unacceptable. This is why availability sits on the top of operational technology security priority under our platform. So the first thing should be availability. Now let's continue. Where OT or operational technology are most of the time are simply attacked by attackers or any advanced persistent threaters. Industrial system face several security challenges. These systems are often operates for almost 50 to 30 years without any replacement. This means an extended life cycle. System remain operational for almost 50 to 30 years without any replacement. Second is It's all about a legacy or any outdated hardware platforms. Thirdly, maintenance window may also be limited, and also that makes patching or updates difficult. And therefore, this flat architecture, and historically, many OT networks were designed with a flat architecture that lacked any strong segmentation. So this factor combined to create a unique security challenge that required a specialized approach aligned with our framework. Next, what are the common operational technology threats? OT threat sources. Several types of threat can target operational technology environment. This will include and ransomware. These are malicious software targeting operational technology system, including ransomware that encrypts critical industrial control system. Secondly, a human error and a misconfiguration, accidental change, incorrect stating, improper system configuration that creates a security vulnerability. Third, the insider misuse, authorized personnel with malicious intent or compromised credential accessing and manipulating operational systems. Those are internal threats. The next is uncontrolled remote access, vendor connection, and a remote access point without proper authentication and authorized control. These are the main cause of threats to the operational technology. Now let us give you some example on industrial technology attack examples. Let's look at the Stuxnet attack on Iran nuclear facility. Let's zoom this. The Stuxnet attack. Let's walk through this visual step by step to understand how the Stuxnet attack incident is demonstrated on the real world impact of cyber attack on industrial control system. The target was on Iran nuclear facility. First, we need to start with industrial environment itself. The target in this case was a nuclear enrichment facility where industrial control system managed thousands of centrifuges used in uranium enrichment. There are various uranium enrichment, as you can see from this sample visual design. This system operated inside what was believed to be secure and isolated industrial network, which is air-gapped facility, meaning it was not directly connected to the outside or any internets. However, air-gapped system can be vulnerable. Then the next stage, we have the air-gapped facility. Then infected USB drive was introduced into the environment using this infected USB device, which was connected to the workstation inside the facility. Then, then someone takes this uninfected USB drive and connect to the workstation inside the facility. Once inside the network, the malware began spreading across Windows computer within industrial controlled systems. Then the next stage is malware spread into the Windows system to compromise the window. But the Stuxnet was not ordinary malware. It was specifically designed to search for a very particular target, industrial control software used to program our PLC controller or the Iran nuclear facility PLC controller, or what we call is that one of the key components of industrial technology, which is PLC controller. So the next stage is PLC infiltration. Then after PLC is compromised, when the malware discovered the correct industrial control system configuration, then it will move to the next stage. The next stage is sabotaging the centrifuge. So it began modifying the logic inside the PLC or the programmable logic controller. These PLC were responsible for controlling the speed of uh, centrifuge used in the uranium enrichment facility. So they want to speed up the what we call the centrifuge activities. Instead of operating normally, the malware instructed the centrifuge to spin at a dangerous speed. That means faking the operation. Then the PLC controlling the speed of centrifuge was sabotaged. Then it will act dangerously at high speed. This means periodically speeding up and slowing down in a way that gradually damage the physical equipment. But the most dangerous part of the attack was deception. While the equipment was malfunctioned, the malware simultaneously sent false data back to the operator monitoring the system. That means making it appear as though everything was operating normally. As a result, the operator had no indication that the centrifuge were being damaged in real time. Eventually, the abnormal operation caused significant physical destruction of this centrifuge equipment. This incident demonstrated that something that had rarely been seen before. I think this is the most famous OT cyber attack that is successfully attempted on OT environment. They could now cause physical damage to the industrial infrastructure. So, as we can see from this whole step, that how the Israeli hackers targeted this Iranian nuclear facility and how they successfully made it. So, cyber attack were no longer limited to stealing data or disrupting a network. This will be a good example of OT attacks. So this is exactly why industrial cybersecurity is so important. Industrial system controls the physical world, like power generation, water system, manufacturing plant, and transportation infrastructure. And securing this system requires specialized frameworks such as SCA, AEC 62443, which we will explore further in this course. Before moving forward, let's test your understanding. In the next slide, you will see several certification style questions related to the industrial cybersecurity fundamental. Please try to answer each question before revealing the explanation. This will help you to reinforce the key concept we discussed in this session. Now that we have completed the foundational concept for industrial cybersecurity, now let's reinforce what we have learned using IC32 style security practice questions. These questions are designed to help you think the way the exam expects you to think, focusing on the concepts, priorities, and the real world reasoning. And also, this is not about memorization. For this question, I recommend you that to pause the video, then choose your answer, then continue to hear the explanation from me. Now let's start with first question. First question says, which statement best describes operational technology or OT? Option A, enterprise business data systems. Option B, system that monitors and control physical process. Option C, network communication system only. Option D, safety reporting systems. Now take a moment and think about what OT actually does in real world. The correct answer is option B. System that monitors and control physical process. Operational technology refers to a system that directly interact with the machine, equipment, and the physical world. Unlike IT system, which is primarily manage information, while OT system influences how physical process behave. This definition is fundamental to the IEC 62443 and its core concept you must understand before moving forward. Now let's look at the second question. Which primary reason OT cybersecurity differ from IT cybersecurity? Which of this option illustrates the major difference between operational technology and information technology? Option A, different operating system. Option B, OT system are isolated. Option C, OT system control physical process. Option D, OT system do not require authentication. Take a moment. The correct answer is option C, OT system that controls physical process. This is the key difference because OT system control real world processes. Cybersecurity incident can affect safety, production, and the environment itself. This is why industrial cybersecurity focuses so heavily on availability and safe operation, not just data protection. Let's move to the next question. Which operational technology component executes control logic? This is simple. First, option A, HMI or human machine interface. Option B, SCADA system. Option C, PLC. Option D, sensor. I think this is the easiest question. So now the correct answer is option C, which is PLC. PLC, which is commonly called to be a programmable logic controller, executes control logic by processing input from sensor and sending the commands to the actuators. Since HMI, this HMI displays information to the operator, while SCADA system just provides centralized monitoring sensors, while sensor is collecting information or data. This is the most important question. This next question is the most important, extremely especially important for the IC32 exam. Which security priority order applies to the OT system? Option A, confidentiality, integrity, availability. Option B, integrity, availability, confidentiality. Option C, availability, safety, integrity. Option D, safety, confidentiality, availability. I think we have discussed about this earlier several times. So the correct option is option C, which is availability, safety, and integrity. In OT environment, keeping system running safely is our top priority. Since data confidentiality is important, but it does not outweigh the need to maintain safe and continuous operation. Since this priority order is the core of IC32 exam concept, and you should remember this clearly. Now let's move to the next option. Okay, why OT system often vulnerable? These OT system are most of the time they are vulnerable. So what is the reason? Option A, short system life cycle. Option B, frequent upgrades. Option C, long life cycle and legacy technology. Option D, excessive encryption. Take a moment to answer this question. So the correct option is which is long life cycle and legacy technology. Many OT systems operate for decades. I think we have already seen from 10 to 30 years without any updates, since they are designed before cybersecurity is even a major concern because of patching and upgrading this system can be risky or disruptive. Vulnerability often remain in place for a long period of time due to this long life cycle and legacy technology. Now let's move to the next. This is a scenario based question which says an automotive manufacturing plant uses PLC, which is a programmable logic controller, to control its production line. After a cybersecurity incident, operator noticed that production has stopped unexpectedly. Then no data appears to be stolen, but restarting the system safely will take several hours. So, what is the most important cybersecurity concern in this scenario? A. Loss of confidential production data. B. Integrity of historical production report. C. Availability of industrial control system. D. Compliance with IT security policies. Which is the most important cybersecurity in this scenario? Just take a moment and think about this scenario. So the correct answer is option so the correct answer is option C, which is availability of industrial control system. In industrial environment, we have already seen that their primary concern is availability and safe operation. Although data confidentiality is very important, the immediate impact of this incident is the loss of production capability. So, any unexpected downtime in production environment will disrupt an operation, cause a financial loss, and also may introduce safety risks during restart or rebooting the system. So IEC 62443 or our framework emphasizes that availability and safety take priority over confidentiality in OT system. Therefore, availability is the most important concern in this scenario. So the correct option is option C, which is availability of industrial control system. Even though no data was stolen, The loss of production directly affects the operation and may introduce safety risk during the restart. I think this scenario reinforces why availability is the top priority in our industrial environment. Let's move to the second scenario question, which deals with the water treatment facility. It says that a water treatment facility uses sensor to measure chemical level and PLC to control dosing pumps. An attacker manipulates sensor data so that the PLC receives incorrect measurement, but the PLC logic itself is unchanged. What is the most likely impact of this attack? A. Loss of operator credential. B. Incorrect physical process behavior. C. Exposure of confidential system documentation. D. Increased network latency. I think take your time. It's all about water treatment facility. The correct answer is option B, which is incorrect physical process behavior, like that of Stuxnet. OT system rely on accurate sensor data to make a control decision. Since OT system rely on accurate sensor data to make control decision, if sensor data is manipulated, then the PLC will still execute this manipulated logic, but based on false information. So this will cause incorrect chemical dosing, unsafe operating condition, and potential impact on public safety. This scenario highlights why integrity of control signal and the sensor data is critical in an industrial cybersecurity, and why OT system must be protected differently from IT system. So the correct answer is option B, incorrect physical process behavior. OT system rely on accurate sensor data. I will repeat it again. OT system rely on accurate sensor data. If the data is manipulated, the PLC will still execute its logic, but based on manipulated or false information. This can result in unsafe chemical dosing and highlighting the importance of protecting sensor data integrity. I think we have finished our question. Now let's finalize our chapter 1. What are our key takeaways throughout these videos? So we have already discussed about OT cybersecurity, which protects the physical world. Operational technology secures industrial processes that directly impact physical system, infrastructure, and safety. Secondly, we have already seen availability and safety are our top priority. Unlike IT, OT system prioritize continuous operation and physical safety over confidentiality. And we have also seen operational technology cybersecurity is different from IT cybersecurity, which is any they have a different requirement. A legacy system operational constraint requires a specialized security approach. We have gained three major concepts. In the next session, we will explore the IEC 62443 standard framework in details. We will examine its structure, governance model, how organizations use it to implement industrial cybersecurity programs. So this will give you the foundation needed to understand how industrial systems are secured in real environment. So we have finished our discussion. Thank you very much. I will see you on the next session. Bye bye.